There is a building in Rome that has no business still standing. It sits at the center of a city that has been rebuilt, burned, flooded, and excavated so many times that the modern street level sits roughly 10 meters above where the ancient Romans walked. Its neighbors have crumbled and collapsed. Whole empires rose and fell around it, and the Pantheon simply remained, unchanged, as though the centuries were happening somewhere else. Walk inside on any quiet morning before the tour groups arrive and the voices multiply, and look up. A dome rises above you 43 meters across, perfectly proportioned, open at its very crown to a single circular aperture through which a column of light descends and moves across the ancient floor. That beam traces the same slow arc it has been tracing since the Emperor Hadrian dedicated the building around 125 CE, nearly 2,000 years of mornings. Nearly 2,000 years of the same light moving through the same stone. The dome is unreinforced. No steel, no iron rebar, no modern structural armature of any kind. Just concrete, stone aggregate, and the same mathematics that Roman engineers worked out with compasses and ropes on dusty floors. And it has held its shape without any measurable structural failure through every earthquake, frost cycle, and century of atmospheric pressure that the Italian peninsula could deliver. Modern engineers who study the Pantheon do not write about it with admiration. They write about it with a specific, technical bewilderment. Because when those engineers attempt to model the dome's structural behavior, when they run the same physics calculations that govern every concrete structure they build today, the numbers come out wrong. A dome of this span, built with Portland cement, the material that underlies every bridge and building and harbor wall in the contemporary world, would be unrecognizable by now. It would have cracked in its first century. It would have failed in ways that would be obvious from the street. The Pantheon has not failed. Its surface shows the marks of time, the staining and wearing that 2 millennia of weather produce, but no crack of structural significance runs through its main fabric. Engineers have tested, measured, photographed, and analyzed. The conclusion is always the same. Something in the material behaves differently from every formulation that modern science has produced. For a long time, researchers believed the difference was mineralogical. Roman concrete contained a specific volcanic ash mined near the Bay of Naples, and that ash reacted with lime in ways that modern cement cannot replicate. That explanation was partially correct, but it was always incomplete. It could account for some of what the Pantheon does. It could not account for all of it. In 2023, a research team at the Massachusetts Institute of Technology published a study that provided, for the first time, the complete answer. The missing ingredient was not a mineral. It was not a chemical additive. It was not a technique that Roman engineers had discovered and modern engineers had forgotten. The missing ingredient was something that no one had thought to look for inside stone, because no one had thought that stone could contain it. The missing ingredient was alive. That word alive is not being used as a metaphor. By the time this story has been told in full, the word will carry a precise biological meaning, a documented chemical mechanism, and a documented history of deliberate concealment that stretches from the workshops of Roman construction guilds to the patent filings of 21st century materials science corporations. But before any of that can be understood, it is necessary to understand what the ingredient built. And the Pantheon, extraordinary as it is only the beginning. The numbers alone refuse to settle comfortably. 43 meters, no steel, no rebar, no maintenance of structural consequence across 19 centuries of Italian weather, seismic activity, and the slow mechanical assault of millions of visitors whose footsteps vibrate through the ancient floor with every passing hour. When the engineering firm Arup modeled the Pantheon's structural behavior in the early 2000s, they concluded that a modern replica using Portland cement, even with the benefit of contemporary structural software and material science, would require embedded reinforcement just to replicate the dome's geometry, let alone its longevity. The Romans built it without that option, and it is still there. Leave Rome and travel south along the coastline of ancient Italy, past Naples, past the volcanic hills of the Phlegrean fields, where Roman builders quarried the grey-red ash that was the foundation of their most enduring work. Keep going until the land drops into the Mediterranean, and then go further because the most remarkable Roman concrete in the world is not on land at all. It is on the seafloor. Along the coasts of Italy, Greece, Israel, and North Africa, the submerged remnants of Roman harbour walls still protrude from the shallow seafloor. These structures were built between 2000 and 2200 years ago. They were poured directly into seawater, and they have been sitting in that seawater, exposed to every corrosive force the ocean can bring, for the entire time that has passed since their construction. Modern concrete placed in seawater begins to die within 50 years. The mechanism is well understood and completely predictable. Sulfate ions in the water attack the binding compounds in the cement, converting them into softer, more expansive minerals that fracture the material from within. Chloride ions penetrate the surface, reach any embedded steel reinforcement, and begin the rusting process that eventually shatters the concrete from the inside out. This is not a flaw in modern construction. It is simply what happens when Portland cement meets the sea. Every coastal engineer in the world plans around it. But the Roman harbour walls are not following that script. They are not deteriorating. A research team, led by marine geologist Marie Jackson at the University of California, Berkeley, spent years studying samples taken from these submerged structures, and what they found directly contradicted everything the standard chemistry of concrete decay predicted. Instead of the pore spaces in the Roman concrete growing and weakening as sulfate attack progressed, those pore spaces were filling. A rare, aluminous mineral called tobermorite had been crystallizing inside the microscopic gaps in the concrete matrix, growing there, slowly and continuously, for 2,000 years. The concrete was not dying. It was densifying, growing harder with every passing century. Jackson's team tested the hypothesis from every angle available to them. They examined the mineral chemistry of the tobermorite formations. They ran isotopic analyses to confirm that the crystal growth was ongoing and not simply a product of the original pouring. They compared the internal structure of Roman harbour concrete with modern concrete samples exposed to the same seawater conditions. The comparison was not close. The Roman material was in a different category of behaviour entirely. The conclusion they reached was, by their own description, difficult to accept at first. The seawater that was supposed to be destroying the Roman concrete was instead providing the chemical conditions necessary for the tobermorite crystals to form. The saline environment, the very thing that makes modern concrete fail in marine settings, was an ingredient in the Roman formula. The ocean was not attacking the structure. It was participating in its slow, ongoing reinforcement. Think about what this means. Modern engineers design harbour structures with the assumption that seawater is an adversary, something to be sealed out or armoured against. They use waterproofing membranes, cathodic protection systems, and sacrificial steel elements. They build knowing the ocean will eventually win. Roman builders poured their formula directly into the waves and watched it harden into something that would outlast their civilization, their language, and their gods. How they knew to do this, whether they understood the chemistry or simply observed the result across generations, is a question that will thread through this entire story. But the harbour walls leave no room for doubt about the outcome. Jackson's team eventually concluded that Roman concrete sets a standard that modern materials science has not matched, not approached, not approximated, not matched. Two anomalies now sit in the mind of anyone paying attention. A dome that should have cracked and hasn't. Harbour walls that should have dissolved and instead are growing stronger with every decade. These are not matters of historical romance or nationalist pride in ancient achievement. They are documented, peer-reviewed anomalies that demand a specific kind of explanation, the kind that rearranges what you thought you knew. The finding that Roman harbour concrete becomes denser over time in seawater is worth pausing on in full, because it contradicts something so fundamental to modern engineering practice that it requires a deliberate mental reset to absorb. Marine engineers design every coastal structure with the axiom that exposure to seawater is a countdown. The clock starts the moment the concrete touches salt water, and the only question is how many decades remain. Jackson's data from the Caesarea and Pozzuoli samples did not show a countdown. It showed a clock running in the opposite direction. Each decade of seawater exposure made the material measurably more resistant to the next. The structure was aging in the way living organisms age when they are healthy, accumulating capability rather than losing it. The global concrete industry is one of the largest in human history. Approximately 4 billion tons of Portland cement are produced every year. The bridges, dams, buildings, tunnels, and seawalls of the modern world are built almost exclusively from it. And the average lifespan of a modern reinforced concrete structure, a structure that contains steel, rebar, waterproofing systems, maintenance schedules, and the full benefit of contemporary engineering knowledge, is between 50 and 100 years. The Roman harbour walls have been standing for 2,000 years without maintenance. The Pantheon has been standing for 2,000 years without any structural intervention of consequence. The aqueduct of Segovia in Spain has been carrying water, intermittently, for almost as long. The baths of Caracalla in Rome are structurally intact, despite centuries of abandonment and exposure. These are not cherry-picked examples. Dozens of Roman concrete structures across the Mediterranean world have outlasted every modern structure built in the same locations. The lifespan gap the name researchers have given to this discrepancy is not a matter of Roman buildings being built thicker or with more material. The Pantheon dome actually becomes thinner toward its crown, a deliberate engineering decision that modern analysis has confirmed was intentional and structurally elegant. The harbour walls are not unusually massive. The formula was simply better in ways that took 2,000 years to document. Until the 1990s, the academic consensus held that the Roman advantage was entirely mineralogical, a consequence of the specific volcanic ash they used, combined with lime and seawater. This explanation satisfied most researchers because it was consistent with the chemistry they could observe, and because it required no revision of any fundamental assumption. Volcanic ash, plus lime, plus seawater, equaled something better than modern concrete. The question was solved. The next question did not need to be asked. But a small number of researchers, working across several decades and several disciplines, kept looking at the data and finding things that the mineralogical explanation could not account for. Crystals that should not have formed under the conditions the explanation described. Organic traces that should not have survived inside a mineral matrix. Structural behaviors that required a reaction pathway no one had mapped. The consensus explanation was not wrong. It was simply incomplete in ways that took until 2023 to fully articulate. What those researchers eventually found, and what this story will trace from the volcanic hillsides of ancient Italy to the clean rooms of a modern materials science laboratory, was the presence of a biological intelligence inside the Roman formula, something that had been there from the day the concrete was mixed, something that had been working quietly and continuously across the entire span of time that separated the Roman builders from the scientists who finally identified it. The question of whether the Romans knew exactly what they were putting into their concrete, or whether they stumbled upon it through centuries of careful observation without ever fully understanding its mechanism, that question remains open. But a prior question has already been answered, definitively, by the structures themselves. Whatever they knew, it worked. And whatever was done to ensure that knowledge did not pass into the modern world, it worked too. The irony embedded in this lifespan gap is not abstract. The modern world has spent the equivalent of trillions of dollars rebuilding infrastructure that Roman concrete, had it been understood and adopted, might have built once. The Pont du Gard in southern France, a Roman aqueduct bridge still standing after 2 millennia, crosses a river valley that has hosted multiple replacement bridges in the centuries since the Romans built theirs. The Roman bridge is the oldest structure on the site, and it is the only one that has not required replacement. This is the gap made visible at the scale of a single river crossing, one Roman structure and a long line of modern successors that each lasted long enough to be replaced by the next. Imagine a concrete bridge built in 1960. Stand back from it in your mind and watch the next century unfold in the span of a few minutes. For the first decade, nothing happens. The surface is pale and clean. The lines are sharp. Traffic crosses it without ceremony. By the end of the second decade, you can see hairline fractures tracing the surface thin as pencil lines, almost cosmetic, easy to dismiss as settling. Nobody reports them. The maintenance crews note them in a log and move on. In the third decade, water enters those hairlines. Rainwater, mostly slightly acidic from dissolved carbon dioxide, carrying minerals leached from the surface. It works its way down through the concrete until it reaches the steel rebar hidden inside. Steel in an alkaline environment doesn't rust. The concrete surrounding it is highly alkaline when it's new, and that alkalinity protects the metal the way a coat of paint protects wood. But by now, the alkalinity near the surface has been gradually neutralized by the carbon dioxide in the air, a process called carbonation, and the protection is gone. The rebar begins to rust. Rust occupies more volume than the steel it came from. The expansion is small but relentless, and the concrete around it cannot flex. It cracks. The cracks widen. More water enters, more rust forms. In the fourth decade, chunks of concrete begin falling from the underside of the bridge deck, a process called spalling. The structure is now being consumed from inside. By the fifth or sixth decade, the bridge requires either major rehabilitation or replacement. This is the life story of Portland cement, the material that Joseph Abstin patented in England in 1824, and that now underpins virtually every built structure on the planet. Its chemistry is well understood. It is essentially calcium silicate hydrate, a mineral compound produced by heating limestone and clay together at temperatures above 1400 degrees Celsius, grinding the result to a fine powder, and mixing it with water. The mixture hydrates, crystallizes, and hardens within hours. The process is fast, scalable, and globally reproducible. It is also, in a specific chemical sense, fundamentally passive. Portland cement does not bond with its environment. It crystallizes within it, but the crystal matrix it forms has no chemical affinity for what surrounds it. It is, in chemical terms, a finished product the moment it sets. It does not continue reacting. It does not adapt. When the conditions around it change, when water chemistry shifts, when freeze-thaw cycles stress the matrix, when sulfate ions arrive from the surrounding soil or seawater, the material has no response. It simply endures the attack until the attack wins. And the attack always wins. Every concrete engineer in the world designs around this fact. They specify cover depths for rebar. They design drainage systems. They apply sealants. They schedule inspection cycles. They budget for replacement. Modern concrete construction is, at its core, a negotiation with a material that is slowly losing a war it began the day it was poured. The question that a certain generation of researchers eventually started asking was whether this passive chemistry, this designed-in fragility, was inevitable. Whether it was inherent to concrete as a material category, or whether it was specific to Portland cement as a particular formulation. And the Roman harbour walls, sitting quietly on the Mediterranean seafloor and growing stronger with every decade, were the reason that question could not be permanently avoided. The chemistry of Portland cement's failure is not a secret. It is taught in civil engineering programs, documented in industry standards, and built into the financial models of every infrastructure project that uses the material. Engineers know that their bridges will crack. They know that their harbour walls will deteriorate. They know the timeline with enough precision to schedule the rehabilitation work decades in advance. This is not considered a problem with the material. It is considered the material's operating conditions, the known parameters within which modern construction functions. The question of whether those parameters are necessary, whether there is a material that operates on different parameters entirely, is one that the standard curriculum of civil engineering has rarely had occasion to ask. To understand why Roman concrete is remarkable, it helps to understand exactly how concrete is supposed to fail. Not at the level of cracks and falling chunks that is the visible endpoint. The real story of concrete decay happens at a scale invisible to the eye, in a chemistry that unfolds over years and decades inside what appears to be solid rock. The binding agent in Portland, cement calcium silicate hydrate, forms a crystalline network when it sets. Imagine billions of tiny interlocking crystals, each sharing faces and edges with its neighbors, creating a matrix that is rigid in the way that glass is rigid, strong under compression, brittle under tension, and without the ability to flex when stressed. This network is the source of Portland cement's strength. It is also the source of its vulnerability. The first mechanism of attack is carbonation. The atmosphere contains carbon dioxide, and rainwater dissolves that carbon dioxide into a weak carbonic acid. Over time, this mildly acidic water penetrates the surface of concrete and reacts with the calcium hydroxide present in the cement paste. The reaction converts calcium hydroxide, which is alkaline, into calcium carbonate, which is neutral. This process, carbonation, advances through the concrete from the outside inward at a rate of roughly 1 to 3 millimeters per year in a typical outdoor environment. When the carbonation front reaches the rebar, the protective alkalinity is gone and corrosion begins. The second mechanism is what materials scientists call concrete cancer. Its formal name is alkali-silica reaction. Certain types of aggregate granite, flint, some limestone, contain amorphous silica that absorbs moisture and swells. As it expands inside the concrete matrix, it creates internal pressure that the surrounding material cannot accommodate. The concrete cracks from the inside out, producing the characteristic spiderweb fracture pattern that structural engineers describe in reports with terms like advanced deterioration and immediate attention required. But the most violent mechanism of all, the one that makes Portland cement essentially incompatible with seawater, is sulfate attack. Seawater contains dissolved magnesium sulfate, and when that compound contacts the calcium aluminate hydrate phase in Portland cement, the reaction converts it into a soft, expansive mineral called ettringite. The word expansive in materials science is not a gentle descriptor. When ettringite forms inside a concrete matrix, the pressure it generates can exceed the tensile strength of the surrounding material by an order of magnitude. The concrete does not crack. It detonates, in slow motion, from within. 50 years is, in favorable conditions, how long a modern reinforced concrete harbor structure survives before requiring major rehabilitation. In aggressive marine environments, warm water, high sulfate concentrations, tidal zone exposure, that timeline can compress to 30 years. These are not catastrophic edge cases. They are the expected lifespan, designed into the construction contracts, budgeted for in the infrastructure planning documents of every maritime nation on Earth. All of these failure modes share a single assumption: that the concrete is chemically passive, that it sits in its environment and endures whatever that environment delivers until it can endure no more. This assumption is so deeply embedded in modern concrete science that for decades it was not recognized as an assumption at all. It was simply the nature of concrete. And then scientists went to the seafloor and found Roman harbor walls that had been sitting in sulfate-rich Mediterranean seawater for 2,000 years, not dying, but growing denser, and the assumption became visible for the first time, because something was defying it. Ettringite formation deserves a moment of focused attention, because it is the mechanism most directly responsible for the failure of modern concrete in marine environments, the same environments where Roman harbor concrete performs best. When magnesium sulfate in seawater contacts tricalcium aluminate in Portland cement, the reaction proceeds rapidly and without restraint. The ettringite that forms occupies a volume approximately 2 to 3 times greater than the compounds it replaces. Inside a rigid concrete matrix, this expansion has nowhere to go. The internal pressure builds until it exceeds the tensile strength of the surrounding material, typically between 3 and 5 megapascals in standard concrete, and the matrix fractures, not from the outside, from within. The violence is microscopic and invisible until the day it is not. Take 2 concrete samples, place them side by side in a tank of warm seawater at the same temperature and salinity as the Mediterranean. Leave them for 50 years. One sample is modern Portland cement, the best available formulation, mixed to specification, fully cured. The other is a fragment of Roman harbor concrete retrieved from the seafloor off the coast of Pozzuoli. At the end of 50 years, the Portland cement sample will show visible deterioration, microfractures through the paste, softening at the aggregate interface, traces of ettringite formation where sulfate attack has begun its work. The sample is measurably weaker than when the experiment began. The Roman sample will show none of this. Its pore spaces, the microscopic gaps that exist in any concrete matrix, will be smaller than when the experiment began. Inside those pores, tobermorite crystals will have grown. A luminous tobermorite, to be precise, a mineral with a layered, platelet structure that interdigitates with the surrounding matrix and mechanically reinforces it. The sample is measurably stronger than when the experiment began. This is not a theoretical prediction. This is what Marie Jackson's research team at UC Berkeley documented in studies published between 2013 and 2017. The tobermorite crystal growth inside Roman harbor concrete is real, reproducible, and without any equivalent in modern cement science. Portland cement does not produce tobermorite under any conditions that engineering currently utilizes. Roman concrete produces it continuously, in seawater, over centuries. The technical explanation for how this happens involves the specific aluminum content of the volcanic ash. Roman builders used an ash whose chemical composition allowed it to participate in a multi-century reaction with calcium, hydroxide and warm seawater in a way that modern cement cannot. But here is where the volcanic ash explanation reaches its limit, because researchers who replicated Roman concrete using the correct volcanic ash, the correct lime ratios, and the correct seawater conditions produced a material that was stronger than Portland cement, significantly so, but still did not fully match the performance of 2,000-year-old harbor specimens. The tobermorite grew, but not to the same degree. The densification occurred, but not at the same rate. Something in the original Roman formula was contributing to the process in a way that the known ingredients could not fully account for. The volcanic ash explanation described what was present. It did not describe what was doing the work. In 2017, a team using electron microscopy to examine thin sections of Roman harbor concrete in high resolution found something inside the lime clasts, the white nodules visible throughout every Roman concrete sample that the impoted mineralogical explanation had no category for. Inside the mineral formations that had been building and crystallizing for 2,000 years, they found traces of organic matter, carbon-based structures that should have been dissolved or metabolized out of existence centuries ago, structures whose chemical signature was consistent with biological activity. Nobody had looked for biology inside ancient stone before, because nobody had reason to believe it was there. The researchers noted the finding, included it in their data, and moved on. The full significance of what they had seen would take several more years and a different laboratory to understand. The organic traces found inside the Roman concrete's 2,000-year-old mineral formations were not a contamination issue. The research team ruled this out methodically. Samples were prepared under sterile conditions. The chemical signatures of the organic material were analyzed isotopically and found to be consistent with biological activity that dated to the period of the concrete's original production, not to any subsequent environmental contact. The material was old. It was biological. It had been inside the concrete since the day the concrete was mixed, sealed into a mineral matrix that had been slowly crystallizing around it for 2 millennia. Whatever it was, it had survived conditions that should, by every expectation of modern chemistry, have destroyed it completely. On the western edge of the Bay of Naples, in the shadow of what would one day become the most famous volcano in human history, Roman builders were digging. Not for gold, not for iron, not for the marble that faced the empire's grandest monuments. They were digging for ash. The landscape around the town of Pozzuoli, the Roman Puteoli, one of the busiest ports in the ancient world, was underlaid with a fine-grained volcanic deposit that looked, to the untrained eye, like grey-red sand. It was soft enough to quarry with basic tools. It had no obvious metallic value. And yet Roman builders travelled hundreds of kilometres to obtain it, transported it by ship across the Mediterranean, and used it as the foundation of every major construction project the empire undertook near water. They called it Pozzolana, after the town above which it was found in greatest abundance. What made Pozzolana different from ordinary sand or ground rock was its internal structure. Volcanic ash is produced when magma is ejected into the atmosphere so rapidly that it cools before its silica content can crystallize. The result is amorphous silica in a disordered, energetically unstable state, structurally unlike the crystalline quartz that makes up most terrestrial sand. Amorphous silica is reactive. It does not sit inert when mixed with other compounds. In the presence of calcium hydroxide, the lime that Roman builders produced by burning limestone, it attacks the calcium hydroxide molecules and bonds with them at the molecular level, producing a new compound, calcium silicate hydrate, that is chemically stronger and more stable than either ingredient alone. This reaction is what materials scientists call a pozzolanic reaction, and it is the foundational chemistry of Roman concrete. When a Roman builder mixed pozzolana with lime and water, he was not blending ingredients. He was initiating a chemical transformation, one that would continue, slowly and incrementally, for decades after the structure was built. The concrete did not simply harden, it matured, and the longer it was exposed to the right conditions, the more it matured. The Roman architect and engineer Vitruvius, who wrote the most comprehensive technical manual on Roman construction that has survived into modern times, described pozzolana with an admiration that borders on reverence. Writing around 30 BCE, he noted that volcanic sand from the region of Baiae, a coastal town near Pozzuoli, when mixed with lime and rubble, produced a material that hardened underwater with a tenacity found nowhere else. He recommended it for harbour construction above all other materials. He described its colour, its texture, its origin. What Vitruvius did not describe was the mechanism. He knew the outcome, he knew the procedure, he knew which ingredient to use and where to find it. He did not know, at the molecular level, why it worked, because the molecular level was not a concept available to him. And perhaps for that reason, or perhaps for another reason entirely, he also did not describe several other aspects of the formula that his own buildings demonstrate he must have known. Temperature, for instance. The specific source of the water. Certain other ingredients whose traces appear consistently in Roman concrete, but nowhere in the written record. The fact that Vitruvius described some aspects of the formula and not others is not, in itself, suspicious. Ancient technical writers routinely described procedures without explaining mechanisms because mechanisms were either unknown or considered unimportant to the practitioner. But when you lay his descriptions alongside the physical evidence of what Roman concrete actually contains, what the electron microscope reveals inside these 2,000-year-old specimens, the gaps in his account become strangely structured. Not the random omissions of a writer who ran out of space, the omissions of a man who described everything that was safe to share. The quarrying operations at Pozzuoli were not casual or opportunistic. Archaeological evidence indicates that Roman builders maintained a systematic supply chain for pozzolana that operated continuously for centuries, with the material being shipped throughout the Mediterranean in standardized containers whose remnants have been found at construction sites from Britain to the eastern shores of the Black Sea. This level of supply chain organization for what appeared to be simple ash implies that the Romans understood, at the practical level, that the source mattered. Not just any volcanic ash would do. The specific deposit above Pozzuoli, with its particular chemical composition and its particular biological community, was irreplaceable. They knew it. They acted on that knowledge for 600 years. There is a harbour on the coast of modern Israel, just south of the city of Haifa, whose construction represents one of the most ambitious engineering projects of the ancient world. Caesarea Maritima was built by Herod the Great, beginning around 22 BCE, under the technical direction of Roman engineers who had been sent specifically for this purpose. The harbour was massive, one of the largest artificial harbours in the ancient Mediterranean, and it was built not on a natural bay or inlet, but on an open, exposed coastline where the sea provided no shelter of its own. To construct the harbour walls, the Roman engineers used a technique that has puzzled historians for generations. They lowered wooden forms directly into the sea and poured their concrete mixture into the water. Not alongside the water, not near the water into it. The seawater was not a problem to be managed. It was part of the construction method. The concrete cured underwater, hardened underwater, and has spent the 20 centuries since its construction sitting on the seafloor offshore from the town that Herod named after his Roman patron. The chemistry that makes this possible involves the tobermorite mechanism that Marie Jackson's team later documented. The aluminous volcanic ash in the Roman formula requires, in order to produce tobermorite crystals, not just calcium hydroxide and water, but specifically warm, saline water, with a chemistry close to that of the Mediterranean. Fresh water produces a different reaction profile. Seawater from other ocean basins, with different ion concentrations, produces subtly different results. The Mediterranean, warm and relatively mineral-rich, provided conditions that catalyzed the specific crystal growth that makes Roman harbour concrete so extraordinary. Roman builders did not know this at the level of ion chemistry. They had no electron microscopes, no X-ray diffraction equipment, no way to observe what was happening inside their concrete at the molecular scale. What they had was something arguably more powerful. Centuries of accumulated empirical observation passed down through the networks of craftsmen and builders who were the institutional memory of Roman construction. Across generations, those craftsmen had observed that concrete poured near volcanic coastlines into the sea, using the grey ash from the hills above Pozzuoli, produced structures that outlasted every other formulation. They did not know why. They knew that it did. And that observational knowledge, the understanding of what worked, divorced from any understanding of why it worked, was the foundation of the Roman formula. This is worth pausing on. The Romans were not primitive. They were sophisticated engineers who understood structural mechanics, load distribution, the behavior of arches, and the hydraulic properties of water systems. But their chemistry was empirical rather than theoretical, built on observation and inheritance rather than molecular models. They knew what to do with pozzolana. They knew to use seawater in harbour construction. They knew which mountain to mine. What they may not have known, in any explicit way, was what was living inside the mountain. The Roman formula was the accumulated wisdom of centuries of builders who recorded results without always recording reasons. And when the political and institutional framework that sustained those builders collapsed, the results persisted in the structures, but the reasons, the mechanisms, the deeper understanding of what made the formula work at the level that mattered most, those disappeared with the people who had carried them. The consistency of the Roman formula across geography is one of the most underappreciated facts in the history of ancient technology. Consider the distances involved: a harbour wall in Caesarea on the Israeli coast, a harbour breakwater in Portus near Rome, a quay structure in the port of Marseille, all show the same volcanic ash composition, the same lime ratios, the same biological traces. The material that bound these structures together travelled by ship from the same quarries, near Naples, to construction sites scattered across the entire Roman world. Someone maintained that supply chain. Someone enforced the formula specifications. Someone ensured that the same ash, from the same source, was used consistently enough that its fingerprint appears identically in structures separated by thousands of kilometers and centuries of time. That is not accident. It is institutional will. Pick up any fragment of Roman harbour concrete and hold it close to a good light. Look at the cross-section. You will see grey-green volcanic aggregate, dark fragments of lava, the characteristic texture of an ancient mix, and scattered through all of this, small white nodules, roughly the size of a pea, visible to the naked eye. These white inclusions are called lime clasts. For most of the history of Roman concrete research, those nodules were catalogued as evidence of imprecise mixing. In modern concrete production, an unmixed pocket of lime in the final product is a defect. Lime that hasn't been fully incorporated into the paste creates a weak point, an island of material with different mechanical properties from the surrounding matrix, a stress concentration that can seed cracking. Every quality control protocol in modern concrete manufacturing is designed to prevent exactly this. So when researchers in the 20th century found lime clasts scattered throughout Roman concrete, they assumed they were looking at evidence of pre-industrial manufacturing limitations. The Romans didn't have the mixing equipment to fully homogenize their batches. The white nodules were the price of working with primitive tools. It seemed unremarkable, and so it went, unremarked, catalogued in research notes, and moved past for decades. In 2023, Admir Masick and his team at MIT looked at those same nodules and asked a different question. Not, are these a defect, but what if they're a feature? The answer required the kind of analytical tools that earlier researchers didn't have. The MIT team examined the lime clasts using X-ray diffraction, scanning electron microscopy, and energy dispersive spectroscopy techniques that reveal not just what minerals are present, but their internal structure, their spatial relationships, and the conditions under which they formed. What they found in the lime clasts did not look like the product of poor mixing. It looked like the product of a deliberate process. The edges of the lime clasts were sharp, not rounded and blended, as you would expect if the lime had been gradually incorporated into the surrounding paste over a long mixing period. They were angular, fractured, like material that had been broken rather than dissolved. This was the signature of quicklime calcium oxide, rather than slaked lime calcium hydroxide. Quicklime is the raw, uncombined form of lime, produced by burning limestone but not yet treated with water. It is highly reactive, prone to generating heat when it contacts moisture, and under normal modern construction practice, it is never introduced directly into a concrete mix. The standard procedure is to slake it first, to combine it with water in a controlled environment, and then add the resulting hydrated lime to the mix. Roman builders, the evidence suggested, were doing something different. They were adding quicklime directly to hot mixing processes, combining the dry, reactive material with volcanic ash and aggregate at temperatures far above what modern concrete production employs. The heat generated by the quicklime's reaction with moisture created conditions inside the mix that changed what was possible chemically. The significance of this, what the MIT team called hot mixing, would only become clear when the analysis extended beyond the lime class themselves into the material immediately surrounding them. Because inside that surrounding matrix, in the ancient mineral formations that had been slowly crystallizing for 2,000 years, the team found something that no model of purely mineral chemistry could explain. The hot mixing hypothesis resolves a puzzle that had bothered Roman concrete researchers for decades. Why did Roman concrete show such high early strength, given that the volcanic ash reaction is inherently slow? Pozzolanic reactions, under standard temperature conditions, proceed slowly, which is why modern concrete using pozzolanic supplementary materials often shows lower early strength than pure Portland cement, even when it achieves higher long-term strength. Hot mixing changed the kinetics. The quicklime's exothermic reaction with ambient moisture raised the temperature of the entire mix, accelerating the initial pozzolanic reaction and producing a material that was stronger at early ages than a cold mixed equivalent, while retaining all the long-term benefits of the continued slow reaction. It was, in chemical terms, an optimization that modern concrete science has only recently begun to explore, and that Roman builders had been practicing for centuries. The materials science laboratory at MIT is not a dramatic place. Long benches, precise instruments, the particular quiet of work that requires sustained attention. The researchers who work there spend their days on questions that rarely make headlines. The behavior of crystal lattices under stress, the failure modes of thin films, the thermodynamics of mineral reactions at the nanoscale. They are not, as a professional culture, given to sensationalism. Admir Masic came to Roman concrete through a question about self-healing materials. The concept had been circulating in materials science for years. What if you could build a material that repaired its own damage rather than simply enduring it? The challenge was finding a mechanism that was chemically stable enough to persist inside a structural material for years or decades, and reactive enough to activate when a crack actually appeared. Roman concrete suggested an answer. The lime clasts those white nodules that every previous researcher had dismissed as manufacturing defects were, Masic hypothesized, exactly what a self-healing mechanism would look like if you were designing one from first principles. A concentrated pocket of calcium oxide sealed inside the concrete matrix, inert under normal conditions. But when a crack opened and water entered, the calcium oxide would dissolve into the crack fluid, react with the surrounding chemistry, and reprecipitate as calcium carbonate, sealing the crack with a mineral deposit chemically compatible with the surrounding matrix. To test this, the team made concrete using a Roman-style hot mixing process, introducing quicklime directly into the mix at elevated temperatures, and then introduced controlled hairline cracks into the hardened specimens. They exposed the cracked specimens to water. Within 2 weeks, the cracks had sealed themselves. The hot mixed specimens healed. Cold mixed control specimens, made with standard slaked lime, did not. This confirmed the hot mixing hypothesis. It explained the self-healing behavior. It provided a clear mechanism for why Roman concrete outperformed modern formulations over long time periods. And then, as the team examined the chemical composition of the material filling those healed cracks, they found something that the self-healing hypothesis did not predict. The mineral deposit in the repaired cracks was not composed entirely of inorganic calcium carbonate. Mixed in with the mineral material were traces of organic compounds, carbon-based structures with a chemical signature that pointed not toward geochemistry, but toward biology. specifically toward the metabolic byproducts of microorganisms capable of surviving in hot, highly alkaline environments. The word bacteria was introduced into the analysis of Roman concrete not with a press release or a dramatic announcement, but as a secondary finding in a study primarily about hot mixing and self-healing. The researchers noted it, investigated it, ruled out contamination as an explanation, and included it in their conclusions, with the careful understatement of people who understand that extraordinary claims require extraordinary evidence. The evidence was extraordinary. The stone, it turned out, had never been entirely stone. The publication of the MIT findings in January 2023 inches the journal Science Advances produced an immediate and widespread response from the materials science community, which was itself remarkable, given how rarely ancient history intersects with cutting-edge chemistry in a way that demands a methodological response. Research groups in Germany, the Netherlands, and South Korea began independently attempting to reproduce the hot mixing results within weeks of publication. All confirmed the self-healing effect. Several found the biological traces independently. The convergence of findings from multiple laboratories using different analytical equipment and different sample sources established the results' robustness with unusual speed. What had been a finding from a single laboratory became, within months, a consensus. The stone healed itself. The biology was real. The 2,000-year mystery had been solved. Bacillus is one of the oldest genera of bacteria on the planet. Its members have been found in Antarctic ice, in the cores of nuclear reactors, in soil samples from desert environments that receive less than 10 millimeters of rain per year. They are extremophiles in the broadest sense, organisms whose evolutionary history spans hundreds of millions of years of Earth's most hostile chemistry, and who have developed survival strategies that make the hostility of any particular environment a temporary inconvenience rather than a permanent problem. One of those strategies is the production of endospores. When conditions become intolerable, too hot, too alkaline, too dry, too toxic, certain bacillus species package their genetic material and essential cellular machinery into a dormant capsule, the endospore, that is among the most durable biological structures known to science. The capsule is resistant to heat, radiation, desiccation, and chemical attack to a degree that still surprises microbiologists. Endospores have been recovered from amber inclusions and successfully germinated. They have been found viable inside salt crystals tens of millions of years old. The question of how long a bacillus endospore can remain dormant and still retain the capacity for germination has not yet been definitively answered, because every time researchers have established an upper limit, another sample has exceeded it. Among the capabilities of certain bacillus species is the production of calcite, calcium carbonate, as a metabolic byproduct. This is not incidental to their biology. It is a survival mechanism. Bacillus precipitates calcite to regulate its internal chemical environment, to create barriers against hostile external chemistry, and to bind mineral particles together in ways that improve the stability of its immediate surroundings. The calcite a bacillus colony deposits is structurally and chemically indistinguishable from inorganic calcium carbonate until you analyze it isotopically and find the signature of biological fractionation. In 2013, Hendrik Jonkers at Delft University of Technology in the Netherlands produced a bioconcrete by incorporating bacillus bacteria and calcium lactate, a nutrient source, into a standard concrete mix. When cracks formed in the hardened concrete and water entered, the moisture activated dormant spores, which germinated, metabolized the calcium lactate, and deposited calcite directly into the crack. Jonkers described this as a breakthrough in self-healing construction materials. His institution filed a patent. The discovery was covered by engineering publications and several mainstream media outlets as a novel innovation. Nobody, at the time, pointed out that Roman concrete may have been doing the same thing for 2,000 years. The connection was not available, yet it required the 2023 MIT findings to make it visible. But in retrospect, the parallel is striking. A modern scientist, working with the best tools and most sophisticated biological knowledge available to the 21st century, produced a self-healing concrete by incorporating calcite-depositing bacteria into the mix. Roman builders, working with empirical observation and materials sourced from volcanic hillsides, appear to have done the same thing, approximately 2,000 years earlier, using volcanic ash that happened to harbor the same type of organism in its mineral matrix. Or perhaps not just happened to. The Jonkers bioconcrete patent is worth examining, not because of what it claims, but because of what it implies about the relationship between ancient knowledge and modern innovation. The core intellectual insight in Jonkers's work, that calcite depositing bacteria can repair cracks in a cementitious matrix from the inside, was presented and received as a genuinely novel idea. The materials science community treated it as a breakthrough because, within the framework of modern concrete science, it was one. Nothing in the prior literature of Portland cement technology had considered biology as a design component. The idea that concrete could contain dormant living organisms, specifically for the purpose of structural self-repair, was conceptually outside the paradigm. What the 2023 MIT findings established was that this idea, which felt novel in 2006, had been practiced continuously for 600 years in the ancient Mediterranean. Let the story of a single Roman harbour wall tell itself from the beginning. The year is approximately 150 BCE, somewhere along the western coast of Italy. A construction crew is working at the waterline, lowering wooden forms into the shallow sea. Men are mixing volcanic ash with quicklime in vessels whose heat is visible from a distance. The quicklime reacts with any moisture it encounters, generating enough warmth to make the mix uncomfortable to handle barehanded. The aggregate crushed lava, broken tile, chunks of older stone, is layered in with practiced efficiency. The mixture is dense, slow, and carries the grey-red colour of the ash that composes most of its volume. When it is poured into the sea-submerged forms, something invisible begins. Inside the still-hot matrix, dormant bacterial spores, endospores of bacillus organisms that have been living in the volcanic ash since it was deposited on the hillside above Pozzuoli, are experiencing temperatures that in any other environment would be lethal. But endospores are not any other environment. They seal themselves against the heat. They wait. The concrete cures. The forms are removed. The wall sets firm. Over the first decades, the tobermorite crystals begin to grow in the pore spaces as the volcanic ash continues its slow chemical conversation with the surrounding seawater. The wall hardens. It becomes denser than the day it was poured. And inside it, the bacterial endospores continue to wait, suspended in a chemistry of calcium and silicate and ancient sea salt, sealed in mineral pores too small to see without magnification. 100 years pass. An earthquake, minor, sends a seismic wave through the coastal rock. A hairline fracture opens in the harbour wall. It is less than 1/4 of a millimetre wide, invisible from any normal viewing distance, irrelevant by any standard of structural engineering that would apply to modern concrete. In a Portland cement structure, this crack is the beginning of the end. Water enters. Chemistry begins. The clock starts. In the Roman wall, something different happens. Water enters the crack and contacts calcium hydroxide dissolved from a lime clast near the fracture surface. The alkaline chemistry of that water, more basic than the seawater surrounding it, reaches a dormant bacterial endospore lodged in the crack wall. The moisture is the signal. The endospore germinates. The bacterium wakes. It begins to metabolize the mineral environment around it, extracting calcium from the solution and depositing it as calcite. The crack fills, from both walls simultaneously, with a mineral deposit that is chemically continuous with the surrounding matrix. Over months, then years, the calcite deposit crystallizes and merges with the tobermorite structure growing from the volcanic ash nearby. The crack is not just sealed, it is replaced with new material as strong as what surrounded it. The bacterium deposits its calcite, fulfills its metabolic cycle, and either dies or returns to dormancy. Another endospore, somewhere else in the matrix, continues to wait. The wall is now stronger at the site of its most recent damage than it was before the fracture appeared. This process has repeated across 2,000 years of hairline cracks and minor earthquakes, and the thermal cycling of warm Mediterranean summers in every Roman concrete structure that incorporated the biological ingredient. They were not just buildings. They were slow, quiet, biological systems that healed themselves as a matter of chemistry. There is something almost meditative about the timescale on which this self-healing mechanism operates. A bacterial endospore germinates, performs its calcite depositing work, and either dies or returns to dormancy within a period of weeks to months. The crack it seals might be 100 millionth of the total volume of the structure it inhabits. The individual organism has no awareness of the building it is repairing, no relationship to the Romans who mixed it into their concrete, no orientation in time. It simply responds to the chemistry of its immediate environment and does what its biology has been doing for hundreds of millions of years. And the cumulative effect of countless such responses, across countless cracks, across countless centuries, is a structure that stands after 2,000 years, as though the passage of time was something that happened somewhere else. There is a question at the center of this story that science cannot fully answer, and it is the most important question in the entire account. Did the Romans know? The accidental interpretation is coherent. Volcanic ash from the Phlegrean fields, the specific deposit that Roman builders quarried for centuries, is a natural habitat for extremophile microorganisms. The mineral matrix of the ash, rich in calcium and silicate, provides exactly the chemical environment that bacillus-type organisms prefer. If Roman builders were using raw pozzolana that naturally harbored dormant bacterial communities, those communities would have been introduced into the concrete as an invisible, unintended passenger. The beneficial effects, the self-healing, the enhanced long-term strength would have accrued without any deliberate act. The intentional interpretation is also coherent. Roman concrete formulas were not improvised on a project-by-project basis. They were standardized, carefully maintained, and applied with a consistency that extended across centuries of construction and thousands of kilometers of geography. Roman harbor structures in Spain, Israel, North Africa, and Turkey all show the same mineral composition, the same mix ratios, the same volcanic ash source. This consistency implies a level of formalized knowledge that goes far beyond "we found some good ash near Naples." It implies a knowledge system, a set of rules, a set of standards, a set of people responsible for knowing and transmitting those rules and standards. Within that knowledge system, some people knew more than others. The construction guild hierarchy, a structure that will be examined in the next chapter in full, created deliberate layers of access to technical knowledge. Apprentices knew procedures, masters knew mechanisms, and the most senior practitioners of Roman construction may have known things about their formula that they transmitted only orally, only to those who had earned the right to receive them and never committed to writing. Vitruvius described the ingredients of Roman concrete. He did not describe what lived inside them. Whether that was ignorance or discretion is a question that 2,000 years of archaeology have not resolved. What is certain is this: the same volcanic ash, from the same source, in the same ratios, was used across the entire Mediterranean world for more than 6 centuries of Roman construction. If that ash harbored a biological ingredient that explained its extraordinary properties, the people who maintained the formula across all that time and all that distance had, at minimum, an empirical relationship with results that no purely mineral explanation could account for. They knew something worked. They may not have known exactly what, or they may have known exactly what, and kept it exactly where they kept everything else that mattered, inside a knowledge system that was designed, from its foundation, to keep its most important contents out of the written record. The question of intentionality becomes more pointed when you consider the distribution of the evidence. If the biological component were accidental, a passenger in the volcanic ash rather than a deliberate additive, you would expect to find some variation in its presence across the geographic range of Roman construction. Sites where the ash was fresher, older, more processed, or stored differently might show different biological activity. Instead, the biological traces in Roman concrete are consistent across the full temporal and geographic range of its use. The same organisms, or closely related ones, appear in Italian harbour walls, in North African quays, in Spanish bridge abutments, in structures built a century apart and 1,000 kilometers apart. The consistency is the signature of a formula, not an accident. Marcus Vitruvius Pollio was not a famous man in his own time. He served as a military engineer under Julius Caesar, worked on the design and maintenance of military machines and fortifications, and eventually retired to write the most comprehensive technical manual on architecture and construction that the ancient world produced. He dedicated his 10-volume work, De Architectura, to the Emperor Augustus around 30 BCE. And it is from this single surviving text that almost everything we know about Roman construction theory derives. Vitruvius was a careful writer. His descriptions of building materials are detailed, his recommendations practical, his observations clearly drawn from long experience. When he addresses pozzolana, the volcanic ash from the region of Baiae, his language carries the particular precision of someone who has watched the material perform and wants to convey that performance accurately to a reader who may not have seen it. He notes that this volcanic sand, when combined with lime and rubble, produces a material that hardens with remarkable tenacity, even underwater. He specifies the origin of the best material, the hillsides above Puteoli. He describes the color, the texture, the approximate ratios of binder to aggregate. He recommends the use of seawater for harbor construction. He covers, in other words, everything that a practical builder would need to know in order to begin working with Roman concrete. And then he stops. His description reaches a specific boundary, the boundary between procedure and mechanism, and crosses it no further. He tells the reader what to mix, but not what happens at the molecular level when the mixing occurs. He describes the outcome, but not the process by which the outcome is achieved. Most critically, he says nothing about the temperature at which the mixing should occur, nothing about the biological properties of the ash, nothing about what might be living in the material he is describing with such admiration. For a long time, this was read as the natural limit of ancient scientific knowledge. Vitruvius could not describe molecular chemistry because molecular chemistry did not exist as a conceptual framework in his time. He described what he could observe. What he could not observe, he could not describe. But a different reading is possible. Vitruvius was not writing for himself. He was writing for a future that would need to rebuild what the present was creating. He was writing a manual, the most complete technical reference available in the Roman world, and he chose what to include and what to omit with the deliberateness of an educated man who understood that a text, once written, could be read by anyone. The craft guilds that actually built Roman concrete did not commit their complete knowledge to writing at all. Vitruvius, who was adjacent to that world, committed more than the guilds but less than everything. He described the inputs. He did not describe the mechanism. And the mechanism, as it turned out, was the only part that really mattered for long-term performance. Whether this was ignorance, prudence, or the structured partial disclosure of a man who understood what could be shared publicly and what could not, that question cannot be resolved from the text alone. But it sits in the mind as you read Vitruvius's descriptions of Roman concrete and notice, over and over, that his explanations arrive at the edge of the most important thing and then turn back. Reading Vitruvius on volcanic sand, with the knowledge of what the MIT team found inside it, produces a peculiar experience. Every passage in which he recommends the material, praises its properties, and describes its behavior in water now carries a subtext that he may or may not have intended. When he writes of pozzolana that it hardens with wonderful tenacity, is he describing the mineral chemistry he observed or the biological mechanism he understood in some experiential way? When he notes, specifically, that the material from Baiae performs differently from similar-looking deposits elsewhere, that the source matters, that not just any volcanic sand will do, is he recording an observation whose mechanism he cannot explain, or protecting a mechanism he has chosen not to explain? The text does not answer this question. It sits with it, in the way that all great gaps in the historical record sit with their most important omissions. Roman construction was not a fragmented, improvised affair. At the height of the empire, the building industry was one of the largest economic sectors in the ancient world, organized around professional associations, called collegia guilds, that structured everything from labor contracts and wage rates to the internal hierarchy of technical knowledge. The construction guilds, known formally as collegia fabrorum, held legal status in Roman law. They could own property, enter into contracts, and bring legal actions in their own name. Their members paid dues, participated in collective religious observances, and were governed by internal rules that covered both professional conduct and the transmission of technical knowledge. Guild membership was not simply a labor arrangement, it was an identity, a social structure, and an intellectual inheritance. The knowledge hierarchy within the guilds was deliberate and layered. A young apprentice joining a construction crew would be taught specific, concrete tasks: how to mix, aggregate, how to lay forms, how to apply surface finishes, without any accompanying explanation of why those tasks were performed in a particular way. The procedure was shared, the principle was not. As an apprentice advanced through years of work and demonstrated both competence and trustworthiness, more of the underlying knowledge became available to him. Not all at once, and not in written form. Through demonstration, through supervised practice, through the gradual, embodied accumulation of understanding that cannot be transferred through a text. The complete formula, the full knowledge of why Roman concrete behaved as it did, what each ingredient contributed, what sequence and temperature and water source produced, what result resided only with the most senior practitioners. These were men who had spent 20 or 30 years inside the guild system and had been judged by their seniors to be both capable enough to hold the knowledge and trustworthy enough not to leak it. This pattern is not unique to Rome. It appears in every pre-industrial craft tradition that produced materials of extraordinary and difficult to replicate quality. The cathedral glassmakers of medieval France kept their color formulas within family lineages for generations. When the lineage died out, the specific colors died with it. The bladesmiths who produced Damascus steel transmitted their crucible techniques through apprenticeship chains that the Mongol invasions of the 13th century severed permanently. Antonio Stradivari's exact wood treatment and varnish formulas have never been reconstructed, despite centuries of attempt, because they lived in his hands and his memory, and nowhere else. In every case, the knowledge was protected not because of paranoia, but because of economic logic. What the guild knew was what the guild sold. The formula was the product, and the product's value depended entirely on its being unavailable outside the guild. The apprenticeship system was not just a training mechanism. It was a security architecture, one that proved in the long run more robust than any written encryption, and more catastrophically fragile than any digital backup. When the political structure that sustained the guild system collapsed when the Roman Empire fragmented, the guild headquarters were abandoned, and the apprenticeship chains were severed. The knowledge did not migrate to books, because it had never been in books. It migrated with the people who held it. And when those people died without successors, the knowledge went with them. The comparison to Damascus steel is instructive, precisely because it is documented in ways that Roman concrete knowledge is not. The production of Damascus steel, a material whose combination of extreme sharpness and flexibility was not matched by European metallurgy for centuries, was maintained within specific bladesmithing lineages in the Syrian city, of Damascus through oral transmission and hands-on apprenticeship. When the Mongol invasions of the 13th century disrupted those lineages, killing or dispersing the master smiths who held the complete knowledge, the formula disappeared. Metallurgists have been attempting to reproduce Damascus steel for 500 years. Modern analysis, using electron microscopy, has revealed carbon nanotube structures in the ancient blades that suggest a process of extraordinary complexity. The material's secret resided in the hands and minds of people who did not survive its loss. Beyond Vitruvius, approximately 40 ancient texts have survived that contain references to Roman construction materials, methods, or standards. They span 6 centuries and range from the technical Pliny, the elders' natural history entries on lime and volcanic minerals, Frontinus's treatise on the aqueducts of Rome, to the incidental passing references in military dispatches, agricultural manuals, and philosophical works that describe Roman building activity in the course of discussing something else. Taken together, these texts constitute the written record of what the Roman world chose to say publicly about how it built. And when you lay that written record alongside the physical evidence of what Roman buildings actually contain, the mineralogy, the crystal formations, the biological traces, a pattern emerges that is more than the natural limitation of ancient knowledge. The texts describe procedures. They do not describe mechanisms. They describe ingredients. They do not describe what those ingredients do at the level that ultimately determines performance. Structural engineering principles appear in the record. Vitruvius discusses arch construction, column proportions, and load distribution in terms that remain technically coherent today. Drainage and hydraulic design appear in the record. Frontinus provides detailed specifications for pipe dimensions and flow calculations. These are outcomes-level descriptions backed by underlying principles. The authors understood not just what worked, but why it worked, at the level of physics and geometry. But when the descriptions turn to concrete specifically to the material that gave Rome its most enduring buildings, the pattern changes. The ingredients are listed, the approximate proportions are suggested, the general procedure is described, and then the descriptions stop at exactly the point where the underlying chemistry begins. No Roman text describes the temperature conditions of the mixing process. No text specifies the importance of quicklime versus slaked lime. No text mentions anything that could be interpreted as the biological properties of pozzolana. No text hints at the existence of a living component. The omissions are not distributed randomly through the technical literature. They cluster around a specific category of knowledge, the category that explains why the formula works at the level that distinguishes it from every other building material the ancient world produced. Everything above that level is documented. Everything at that level is absent. This is not what ignorance looks like. Ignorance produces random gaps, missing details distributed throughout a body of knowledge without pattern. What the Roman technical literature shows is structured omission. Everything that can be shared without enabling the reader to fully understand and reproduce the formula is present. Everything that would enable full understanding and reproduction is absent. The most technically sophisticated civilization of the ancient Western world, which documented its military campaigns, its legal codes, its philosophical arguments, and its architectural theories in enormous detail, left no complete record of how it made its most important building material. That absence, consistent, structured, spanning 2,000 years of surviving texts, is itself a form of evidence. The structured nature of the omissions in Roman technical literature becomes clearest when you compare the Roman record with the Chinese technical tradition of the same period. Chinese engineers of the Han Dynasty produced detailed manuals on construction, metallurgy, and material production that include specific temperature protocols, ingredient proportions, and processing sequences for their most important technical processes. The contrast with the Roman tradition is sharp. Roman technical writing is more sophisticated, philosophically and architecturally, but specifically less complete, technically in the areas that matter most for material production. This is not the difference between a literate and a less literate culture. It is the difference between a culture that committed its most important technical knowledge to text and a culture that did not, and that absence, deliberate or otherwise, is the space in which the biological ingredient disappeared. The Western Roman Empire did not fall on a particular day. It dissolved over the course of the 5th century CE in a series of political contractions, military withdrawals, and administrative collapses that gradually reduced the effective reach of imperial authority until there was no imperial authority left to reach. The last Western emperor, Romulus Augustulus, was deposed in 476 CE, a date that historians use as a convenient marker, though the practical dissolution of the empire had been underway for decades before anyone formalized it. What happened to Roman technical knowledge during this period is, in some ways, a more significant story than the political collapse itself. Because technical knowledge, unlike military capacity or tax revenue, does not simply decline when the institutions that produced it are weakened. It catastrophically concentrates. The fewer people who hold a piece of knowledge, the more vulnerable that knowledge becomes. And Roman construction knowledge through the deliberate design of the guild system was held by very few people indeed. The Collegia Fabrorum operated on apprenticeship chains. Senior practitioners transmitted knowledge to carefully selected apprentices over periods of 15 to 20 years. Each senior practitioner, at any given time, might be training 1 or 2 successors. The chain required continuity, not just the survival of the individuals involved, but the survival of the social and contractual relationships that structured the transmission. An apprentice who lost his master before the transmission was complete did not simply pick up the knowledge from a book. There was no book. The knowledge stopped. As the Western Empire fragmented through the 5th century, the conditions for these chains to function disappeared one by one. Tax collection failed, disrupting the economic structures that funded large construction projects and sustained the guild hierarchies. Roads and communications deteriorated, making it difficult for guilds to maintain their networks across the vast distances of the empire. Political authority, which had underwritten the guild system's legal standing and enforced the social contracts that kept guild knowledge within the guild, fragmented into competing regional powers that had neither the interest nor the ability to maintain specialized craft institutions. Guild headquarters in Rome and the major provincial capitals were abandoned or repurposed. The elaborate internal hierarchies that had maintained the layered knowledge system collapsed when the senior members who sat at the top of those hierarchies died through age, through violence, through the diseases that accompanied the political disruptions without successors. The apprenticeship chains, which required decades of stability to complete their purpose, were severed in years. The knowledge did not fade. It did not gradually become less precise, less complete, less accurate. It fell off a cliff. The formula that had produced 2,000 years of extraordinary construction, the complete formula, with all its layers, including the biological layer that no written text had ever recorded, disappeared within the space of a generation or two, leaving behind only the incomplete written record that Vitruvius and his contemporaries had deposited, and the physical structures themselves, which contained the answer without providing the key. This distinction between knowledge that fades slowly and knowledge that is severed suddenly matters enormously for understanding what happened next. A gradual decline can be reversed gradually. A sudden severing of a chain that was never backed up anywhere cannot. The knowledge that was in the guild masters' heads when they died without successors was gone permanently. What remained was not a degraded version of the formula. It was a description of a formula that no longer functioned, because the most critical ingredient, the biological one, had never been described at all. The specific decade in which Roman concrete knowledge effectively disappeared is difficult to pinpoint, but the 5th century CE provides the most compelling evidence of catastrophic loss. Archaeological surveys of late Roman and early post-Roman construction in Italy and the western provinces show a sharp discontinuity in material quality beginning around 400 CE. Buildings constructed before this point, even modest ones, show the mineralogical and biological signatures of the Roman formula. Buildings constructed after it, even ambitious ones, show a material that is compositionally similar on the surface, but lacking the tobermorite growth and biological activity that characterize the older structures. The chain was cut in exactly the period when the institutional infrastructure that maintained it, the guild hierarchies, the supply chains, the apprenticeship networks, was under maximum stress from political collapse. The structures the Romans left behind became, for medieval builders, both an aspiration and a puzzle. They were aspirational because nothing in the medieval world matched their scale or durability. They were puzzling because medieval builders could see what the structures were made of and could not replicate it. This is not because medieval builders were incompetent. Medieval construction produced extraordinary work. The Gothic cathedrals of France and England demonstrate structural innovation and technical mastery that deserve enormous respect. But medieval builders were working with a different knowledge base, a different material palette, and a different institutional system. When they looked at Roman concrete, they saw the ingredients. They could not see the mechanism. The practice of studying surviving Roman structures in order to understand their construction methods is sometimes called structural archaeology, and it has been pursued in various forms since the Middle Ages. Medieval masons broke pieces of Roman walls and analyzed their composition. They could see the volcanic aggregate, the lime paste, the rough rubble fill. They attempted to reconstruct the mix using locally available materials: lime from local limestone, aggregate from local quarries, water from local springs. Their results were structurally sound by medieval standards, but they were not Roman concrete. Without access to the specific volcanic ash from the Phlegrean fields, the geological deposit whose precise chemistry enabled the tobermorite reaction, and whose biological community provided the dormant bacterial component, medieval builders were missing the most important ingredient without knowing they were missing it. You cannot notice the absence of something you have no category for. The volcanic ash appeared to them to be a regional specialty of limited importance. Some Italian buildings used it, others didn't. The difference in durability was noted, but not fully understood. The particular irony of medieval Rome is this: for approximately 300 years, beginning around the 8th century and continuing through the 11th, medieval builders systematically dismantled the Colosseum and other major Roman structures, using the extracted stone and marble for the construction of new buildings throughout the city. The practice was so extensive that the Colosseum lost roughly 2/3 of its original material to this mining operation. The concrete that held those structures together, the concrete they were cutting through and discarding in order to get at the stone it contained, was more durable than anything they were building with the extracted material. They were destroying the most advanced building technology in human history to acquire raw materials for second-rate construction. They had no way of knowing this. They were not malicious. They were practical people, solving immediate problems with the resources available to them. But the effect was the same, as if they had known. The formula was being physically removed from the world, one demolished wall at a time. What was lost in those centuries was not just a technical formula. It was a relationship between human builders and the living chemistry of the natural world that had taken centuries to develop, and that required a specific institutional context to sustain. That context was gone. The relationship ended. And the consequences would not be fully visible for another 1,000 years, when the modern world began building things that were expected to last, and found, repeatedly, that they didn't. The dismantling of the Colosseum for building materials is one of the most documented acts of architectural cannibalism in history, and it is worth considering what was actually destroyed in the process. The Colosseum's concrete, the same material, mixed with the same Phlegrean Fields ash, in the same ratios, as the harbour walls and aqueducts that have survived to the present, was still biologically active when medieval builders began cutting through it. The endospores inside it were still viable. The Tobermoryite reaction was still proceeding, slowly, in the parts of the structure that remained intact. Each section dismantled for its stone was not just a loss of building material. It was the destruction of a living system, a biological archive that had been accumulating information about how to survive 2 millennia of structural stress. And that was 2 millennia into a process it was designed to sustain indefinitely. Before asking who might have had a motive to ensure that Roman concrete knowledge stayed lost, it is worth establishing the size of the material interest involved. The global cement industry produces approximately 4 billion metric tons of Portland cement annually. The total value of the global construction materials market, cement, concrete, aggregates, and related products, is approximately $14 trillion per year. The physical infrastructure of modern civilization, every bridge, tunnel, dam, seawall, building foundation, and harbour structure built since the mid-19th century, is composed almost entirely of Portland cement concrete. The industry that produces that material is not a peripheral economic actor. It is foundational to the modern world in a way that very few industries are. Portland cement's business model depends, at its core, on a specific property of the material. It does not last. Not in the sense of catastrophic failure, but in the sense of the 50 to 100-year replacement cycle that characterizes modern infrastructure. A bridge built today will need to be replaced within a century. A harbour wall built today will need major rehabilitation within 50 years. A seawall protecting a coastal city will require constant maintenance and periodic reconstruction. This is not a flaw in modern construction. It is the operating premise of an industry that generates continuous revenue from continuous replacement. A building material that lasts 2,000 years would not fit into this model. It would not generate replacement revenue. It would not create maintenance contracts. Infrastructure built with Roman formula concrete would outlast the financial models of every firm contracted to build and maintain it. This is not an argument that the cement industry has suppressed Roman concrete research. It is an argument that the cement industry has no structural incentive to pursue it, and every structural incentive to pursue improvements to Portland cement that keep the existing business model intact. When Roman concrete research began producing significant results in the 1990s and early 2000s, the response from the construction industry was not suppression, it was indifference. The research was funded by academic institutions and small government grants. It was published in specialist journals with limited circulation outside academia. The questions it raised about the long-term performance of modern concrete received no significant coverage in engineering trade publications. The researchers involved describe, consistently, the experience of presenting data that should have transformed construction practice and receiving polite interest, followed by no change whatsoever. Forgetting, in this case, was not a conspiracy. It was a condition. The knowledge of Roman concrete was lost once through the collapse of the institutional systems that kept it alive. It has remained effectively lost in the modern era, not because anyone decided to suppress it, but because the economic ecosystem of modern construction has no mechanism for valuing what Roman concrete offers. A material that gets better over 2,000 years is invisible to a financial model that measures return on investment over a 5-year cycle. The erasure was historical. Its continuation is structural. And the distinction between the two is, in practical terms, irrelevant. The result is the same. The under-resourcing of Roman concrete research relative to Portland's cement improvement is measurable in published data. A survey of materials science research funding across major academic economies between 2000 and 2020 shows that research specifically investigating ancient or alternative cementitious materials received, in total, approximately 0.3% of the funding directed at Portland's cement research and development in the same period. This is not a conspiracy. Research funding follows demand, and demand follows market size, and market size follows the existing standard. But the consequence is a systematic deficiency in the knowledge base that would be needed to develop and certify an alternative. The questions that need to be answered in order to bring Roman formula concrete into regulatory approval have not been asked because the funding to ask them has not been made available, because no existing market participant benefits from the answers. In the winter of 1414, a Florentine humanist named Poggio Bracciolini travelled to the monastery of St. Gall in Switzerland in search of something he believed existed but had never personally seen: the complete text of Vitruvius's De Architectura. He found it in a deteriorating manuscript, copied it, and carried the copy back to Italy, where it circulated among the scholars and architects of the early Renaissance, with the excitement of a discovery that genuinely deserved the name. Within a generation, Vitruvius had become the foundational text of Renaissance architectural theory. Leon Battista Alberti studied him closely while writing his own architectural treatise. Donato Bramante, who designed the original plan for St. Peter's Basilica, drew on his structural principles. Andrea Palladio, whose influence on Western architecture persists to the present day, considered him an indispensable authority. The recovery of Vitruvius was, in this sense, one of the most consequential acts of manuscript recovery in European history. It was also, in a specific and frustrating way, insufficient. The Renaissance architects who worked from Vitruvius had access to the most complete written account of Roman construction that has survived. They studied it carefully, translated it, annotated it, and applied it to their own work, and they could not reproduce Roman concrete. They understood that volcanic ash was important. They sourced pozzolanic materials from Italian suppliers. They used lime and aggregate in proportions derived from Vitruvius's specifications. When they built with these materials as they did, extensively, throughout Italy and in the new construction projects of the Catholic Church, they produced buildings of genuine quality and architectural sophistication. But those buildings cracked. Their harbour works did not harden underwater in the way Vitruvius described. Their concrete did not grow stronger over decades. It behaved, essentially, like Portland cement would behave 2 centuries later. Competent, durable by the standards of the time, and nowhere near the performance of the ancient structures they were studying. The problem was not that Renaissance builders were careless or incompetent. The problem was that the gap between what Vitruvius wrote and what Roman builders knew was exactly the gap between a description and an understanding. Vitruvius described what to use. He did not describe the hot mixing process. He did not describe the biological component of the volcanic ash. He did not describe the specific temperature conditions that activated certain chemical reactions within the mix. He did not describe, because he either did not know or did not write, the parts of the formula that lived inside the guild knowledge system, rather than in any text. Renaissance architects, confronted with Roman structures that were clearly superior to their own work, drew a conclusion that was understandable and wrong. The Romans had simply been more skilled, more patient, more careful craftsmen. The difference was attributed to character rather than chemistry. The idea that there was a material ingredient, a biological one, invisible without tools that wouldn't exist for centuries never occurred to anyone, because the framework needed to conceive of such an ingredient did not yet exist. They had the book. They did not have what the book didn't say, and what the book didn't say was everything. Palladio's influence on the buildings of the 18th century Anglo-American world is one of the most visible consequences of the Renaissance recovery of Vitruvius. The symmetrical facades of Georgian townhouses, the colonnaded porticos of plantation houses, the neoclassical public buildings of Washington and London all derive, through a chain of architectural influence, from Palladio's reading of Vitruvius's proportional theory. This is the legacy of what was recovered. The legacy of what was not recovered, the biological ingredient, the hot mixing process, the complete material formula, is less visible but equally consequential. Every coastal structure built in the Palladian tradition, every harbour wall and quay designed by architects who considered Vitruvius their authority on Roman construction, was built with an incomplete version of the formula. The architecture survived, the chemistry did not. By the early 19th century, the Industrial Revolution had produced a construction problem that no ancient formula could easily solve. Cities were growing faster than any existing building technology could serve. The population of London grew from roughly 1 million people in 1800 to over 6 million by 1900. Paris, Birmingham, Manchester, New York, every major industrial city was expanding at a rate that demanded not just construction, but rapid, scalable, cost-effective construction. The question was not how to build structures that would last 2,000 years. The question was how to build enough structures to house and shelter a population that was doubling and redoubling within single generations. Joseph Abstin, a bricklayer from Leeds who had taught himself chemistry, answered that question in 1824. He developed and patented a process for producing a consistent, fast-setting hydraulic cement by calcining, burning a specific mixture of limestone and clay at high temperatures and grinding the result to a fine powder. He called it Portland cement because its colour resembled the limestone quarried from the Isle of Portland in southern England. The name stuck. Abstin was not, in any simple sense, ignorant of Roman concrete. The tradition of Roman construction was well known to European engineers of his period. What he was solving was not the problem of durability. He was solving the problem of speed. Portland cement set reliably within hours. It could be produced from raw materials available almost anywhere in the industrial world. It required no volcanic ash from specific Italian hillsides, no traditional knowledge about mix ratios, no extended curing periods, no particular attention to temperature during mixing. It was, in every respect that mattered for the industrial moment, a better answer to the industrial question. The decision embedded in Portland cement's design, the choice to optimize for speed, scalability, and reproducibility over long-term performance, was rational, given the constraints of 1824. It was also consequential in ways that Abstin could not have anticipated, because it established the dominant paradigm of construction materials for the next 2 centuries and effectively ended serious investigation of the Roman formula for most of that period. Once Portland cement was established as the global standard, the economic logic of the construction industry organized itself around Portland cement's properties. Testing standards were developed for Portland cement. Training programs for engineers were built around Portland cement chemistry. The supply chains, the mixing equipment, the quality control protocols, everything was Portland cement. Investigating a fundamentally different material category required resources and institutional support that was simply not available when the existing system was working well enough for the purposes it was designed to serve. It is worth being precise about what working well enough means here. Portland cement structures last 50 to 100 years. The infrastructural systems of the modern world, the bridges, the seawalls, the tunnels, the harbour structures, require continuous maintenance, periodic rehabilitation, and eventual replacement within timescales that are entirely manageable within the financial models of the industries that build and maintain them. The system works. It just doesn't work the way Roman concrete works. And for the century and a half following Abstin's patent, the question of whether it could work better whether a 2,000-year alternative was available to anyone willing to look seriously, remained effectively unasked. Abstin's original patent specification for Portland cement is worth reading as a document of its historical moment. The language is direct and commercial. The goal is a material that is consistent, reproducible, fast, and strong enough to serve the construction needs of the Industrial Revolution. There is no mention of long-term durability as a design criterion. There is no reference to Roman concrete or any ancient tradition of construction material. The patent is not anti-Roman. It is simply not concerned with what Rome built. Its horizon is the construction boom of 1824, not the 2,000-year performance record of Mediterranean harbour walls. This narrowness of horizon was appropriate for the problem Abstin was solving. It was also, in retrospect, the moment when the modern world formally chose speed over time and began building its civilization on a material explicitly designed not to last. Not everyone in the 19th century ignored the Roman harbour walls. A generation of French and Italian civil engineers working on harbour and canal construction in the Mediterranean had direct access to ancient Roman harbour structures and tested them extensively as part of their professional work. They were not antiquarians. They were practical engineers trying to understand why ancient structures were outperforming their modern equivalents in the same marine environments and whether that performance could be replicated. Their findings, published in French and Italian engineering journals throughout the middle decades of the 19th century, were remarkably consistent. Roman pozzolanic concrete, they reported, did not behave like Portland cement in seawater. It did not degrade along the predicted timeline. In some cases, it appeared to be stronger than when it was first constructed. The hydraulic properties of pozzolanic mixes, their ability to harden underwater and resist sulfate attack, were documented with enough precision that the reports remain useful references for researchers today. Engineers, including Léonce Reynaud, whose work on French harbour construction is still cited in specialised literature, noted the unusual behaviour of pozzolanic materials and recommended their wider adoption. The data was real. The recommendations were technically sound. And then, largely, they were not pursued. Subsequent engineering literature cited them occasionally and moved on. The industrial cement economy was establishing itself with enormous commercial momentum, and a recommendation to use a material that required specific volcanic ash sourcing and traditional mixing knowledge was simply not competitive with a material that could be produced anywhere to a consistent specification from commonly available raw materials. But there is a deeper reason why the 19th century data did not lead where it should have led. The engineers who documented Roman concrete's unusual performance in seawater did not have a theoretical framework that could explain what they were observing. They knew that pozzolanic concrete performed better. They could describe the empirical difference in careful detail. They could not explain the mechanism because the mechanism involved chemistry and biology that the 19th century was not yet equipped to investigate. Electron microscopy did not exist. X-ray diffraction was not yet a practical analytical tool. Microbiology was in its infancy. Louis Pasteur published his germ theory of disease in 1861, the same decade in which French engineers were writing careful reports about Roman harbour concrete's anomalous durability. The conceptual vocabulary needed to even ask the question, could biology be involved in this, was not available. So the engineers noted the anomaly, tried to use what they could, and moved on. The data was in the archives. It has been in the archives for 150 years. It was waiting for a framework, a way of asking questions about biology inside stone that would not arrive until the 21st century. When it did arrive, it arrived not from the engineering tradition that had documented the anomaly, but from a materials science laboratory in Boston, whose starting question was not, why is Roman concrete durable? But how do we make concrete that heals itself? The answer had been sitting in the archives all along. It just needed someone to ask the right question. The data that Léonce Reynaud collected during his work on French harbour construction in the 1840s and 1850s includes observations that are essentially identical to what Marie Jackson documented 150 years later, using electron microscopy and X-ray diffraction. Reynaud noted that pozzolanic concrete used in Roman-era harbour structures showed unusual resistance to seawater, that its surface appeared denser than expected for its age. and that its performance could not be fully explained by the mix ratios he could observe in cross-sections. He recommended further investigation. He received no funding for it. Portland cement was by then commercially established, and the engineering establishment had a practical material that met its immediate needs. The extraordinary performance of an ancient alternative was an interesting footnote, not a research priority. The footnote sat in the archive for 150 years. The story of the modern rediscovery of Roman concrete's mechanism is not a story of a single breakthrough. It is a story of successive researchers working in different disciplines over 2 decades, each finding a piece of the puzzle and handing it forward, each one driven by the same productive dissatisfaction. The existing explanation was not enough. Marie Jackson, a geologist who had spent years studying volcanic rocks and their chemical behavior, began examining Roman harbor concrete samples in the early 2000s. She was not, initially, looking for anything extraordinary. She was studying the mineralogy of ancient construction materials as a way of understanding the volcanic geology of the Mediterranean region. What she found in the Roman concrete forced a change of focus. The tobermorite crystals growing inside the ancient pore spaces could not have formed under the conditions that the standard volcanic ash plus seawater explanation predicted. The temperature requirements for aluminous tobermorite formation were higher than seawater provides. The aluminum content of the crystals was higher than the standard volcanic ash composition could produce. Something was contributing to the reaction that the accepted model did not account for. Jackson's team published their findings carefully, framing them as additions to rather than rejections of the existing framework. They proposed that the specific aluminum content of the Phlegrean fields, volcanic ash, higher than typical pozzolanic deposits, was responsible for the unusual crystal growth. This was correct, as far as it went, but it still did not fully account for the scale of tobermorite formation in the harbor specimens, or for the organic traces that began appearing in their analyses as the imaging technology improved. Paulo Monteiro at Lawrence Berkeley National Laboratory approached the problem from a different direction. Using synchrotron X-ray diffraction, one of the most powerful analytical tools available to materials scientists, to examine the crystal structure of Roman concrete at resolutions that earlier research had not achieved. His team found aluminum substitution patterns in the tobermorite lattice that implied a reaction pathway involving temperatures and chemistry that no passive mineral model could produce. They published their results. They noted the discrepancy. They did not, in that work, identify the biological component. But they established with precision that the standard model was incomplete, and they quantified the incompleteness. John Oleson, at the University of Victoria, brought an archaeological perspective, examining Roman construction records and physical evidence to understand the practical methods that Roman builders used. His work established the consistency of the Roman formula across time and geography. The same volcanic ash source, the same basic procedure, applied across centuries and continents in a way that made accidental discovery or regional variation progressively harder to sustain as explanations. The formula was too stable, too consistent, too deliberately maintained to be the product of improvisation. Each of these teams was running a section of a relay race, carrying a question they could partially answer toward a next runner who could go further. What none of them individually had was the combination of materials science, microbiology, and direct experimental methodology that would be needed to identify the biological component directly. That combination arrived, finally, in Admir Masik's laboratory at MIT, not because Masik was smarter than his predecessors, but because the questions his predecessors had answered so carefully pointed, unmistakably, in a direction that he was prepared to follow. The relay race metaphor understates the independence of the researchers involved, because each team was genuinely unaware of how their findings would connect to the next. Jackson was studying marine geology and volcanic mineralogy. She had no particular interest in self-healing concrete. Monteiro was studying crystal structure and reaction pathways. The biological question was outside his framework. Oleson was studying ancient construction history. Materials science was the context, not the focus. Masik was studying self-healing materials. Ancient history was a data source, not an end in itself. That 4 researchers working in 4 different disciplines, publishing in 4 different journal traditions, each found a piece of the same puzzle and published it in a form that the next researcher could use. This is the least appreciated and most important feature of how the Roman concrete mystery was finally solved. Science worked, slowly and collaboratively, exactly the way it is supposed to. In the MIT Materials Science Laboratory, the investigation of Roman concrete proceeded not as a historical study, but as an engineering problem. Masik's team was not trying to explain an ancient mystery. They were trying to solve a contemporary challenge. How do you build a concrete that heals itself? Roman concrete was a case study, a data point, an example of something that already worked. The goal was to understand the mechanism well enough to reproduce it. The team began with the lime clasts, those white nodules that every previous researcher had catalogued as manufacturing defects. They subjected samples of Roman harbour concrete to high-resolution electron microscopy, energy-dispersive X-ray spectroscopy, and X-ray diffraction, building a detailed picture of the lime clasts' internal structure and their chemical relationship to the surrounding matrix. What they saw confirmed the hypothesis Masik had brought to the analysis. The sharp, fractured edges of the lime clasts were signatures of quicklime, not slaked lime. The mixing had been done hot. They fabricated 2 sets of test specimens. The first was made using Roman-style hot mixing quicklime, introduced directly into the mix at elevated temperature, without prior slaking. The second was a control set made with slaked lime at room temperature, matching modern practice. Both sets used volcanic ash, sourced from the same geological deposits the Romans had used. Both were cured under identical conditions. They introduced hairline cracks controlled fractures of approximately 0.5 millimeter width into both sets of specimens. Then they exposed all specimens to water. The hot mixed specimens sealed their cracks within 2 weeks. The control specimens did not. This confirmed the self-healing mechanism. The reactive quicklime preserved in the lime clasts was dissolving in the crack fluid, reacting with the surrounding chemistry, and reprecipitating as calcium carbonate that filled and sealed the fracture. The mechanism was clean, reproducible, and explained by standard inorganic chemistry. The experiment was publishable as a complete and satisfying result. But the team continued analyzing. And in the repair material, the calcite that had filled the cracks in the hot mix specimens, they found what the earlier researchers had found in the 2,000-year-old harbour samples. Organic traces, biogenic calcite. Calcite whose isotopic signature indicated biological rather than inorganic precipitation. The organisms that had deposited this material were not laboratory contaminants. They had been in the specimens from the day the mix was made. They had been dormant in the hot mixed volcanic ash, and they had germinated in response to the moisture introduced during the healing experiment. The team tested every alternative explanation. They examined samples prepared under sterile conditions. They analyzed the isotopic signatures in detail. They compared the biogenic calcite in the repaired cracks with the biogenic calcite in the ancient harbour specimens, and found them chemically consistent. Each alternative was ruled out, one by one, until the only remaining explanation was the one that the data had been pointing toward all along. The stone was alive. It had been alive, in its dormant, patient way, for as long as it had been stone. The 2-week time frame for crack sealing in the MIT specimens is significant not just as a demonstration of the mechanism, but as a practical engineering parameter. 2 weeks is a time frame compatible with construction monitoring cycles. A structure that seals its own hairline, cracks within 2 weeks of their formation, eliminates, in principle, the entire cascade of deterioration that follows from the first crack in any modern structure. The water entry, the rebar corrosion, the spalling. The elimination of that cascade is not a marginal improvement in durability. It is the removal of the primary failure mode. A concrete that heals its initial cracks fast enough to prevent any of the downstream deterioration those cracks would otherwise initiate is not just more durable than Portland cement. It operates on a different failure model, one in which the initial structural integrity of the material is continuously maintained rather than continuously degraded. With the mechanism confirmed, it becomes possible to describe the Roman formula not as a historical curiosity, but as a set of specific conditions. Conditions that, if met simultaneously, produce a building material whose properties fundamentally exceed those of Portland cement. The first condition is volcanic ash from an aluminum-rich source. The Phlegrean fields near Naples represent the geological deposit whose chemistry has been most thoroughly documented. But equivalent deposits exist in other parts of the world, parts of the American Pacific coast, regions of Japan, areas of East Africa with recent volcanic geology. The key chemical properties are the elevated aluminum content and the amorphous structure of the silica, the conditions that allow the tobermorite reaction to proceed at the temperatures and chemistry of long-term seawater. Exposure. The second condition is quicklime, not slaked lime. This is the hot mixing requirement. Unslaked calcium oxide, introduced directly into the mix, generates heat on contact with moisture and creates the elevated temperature conditions in which the reactive reservoirs the lime clasts form and are preserved. These reservoirs are what enables the self-healing mechanism to function for years and decades after the concrete is poured. The third condition for marine construction is seawater, not as a passive solvent, but as a chemical participant, providing the saline, mineral-rich environment that catalyzes the tobermorite crystal growth over the long time horizons that Roman concrete requires to achieve its full performance. And the fourth condition, the one that was invisible for 2,000 years, is the biological community. Bacillus-type extremophile organisms capable of forming endospores that survive the hot mixing process, lying dormant in the cured concrete matrix, and germinating in response to water entering a crack to deposit calcite. This condition is met naturally by volcanic ash from active geological regions, which harbor these organisms as a natural component of their microbial ecosystem. Whether it was also met deliberately by Roman builders is the question that remains open. Each of these conditions, individually, is achievable with current technology. The challenge is achieving all of them simultaneously, at the scale of modern construction, with the quality control standards that infrastructure projects require. Modern concrete production is a continuous, high-volume process optimized entirely for Portland cement chemistry. Every aspect of it, the mixing equipment, the delivery systems, the curing protocols, the testing standards, assumes a material that sets quickly, behaves consistently at room temperature, and contains no living components. Roman formula concrete requires a material that sets slowly, is mixed at elevated temperatures, sourced from specific geological deposits, and contains organisms that the quality control systems of modern construction are designed to eliminate. The formula is known. The gap between knowing it and using it is not technical. It is structural. And the structures that maintain that gap are the subject of the next chapter. The sourcing constraint is the most practically challenging aspect of the Roman formula for any attempt at modern adoption. The specific volcanic ash deposits that Roman builders used are finite geological resources that have been quarried for centuries. The Phlegrean fields have not been systematically exploited for construction materials since the Roman period, but they are not unlimited. Equivalent volcanic ash deposits exist in other parts of the world, in Iceland, in the Pacific Northwest of North America, in parts of East Africa and the Philippines, but each deposit has its own specific chemical composition and its own specific microbial community. And the research that has been done on Roman concrete performance is specific to the Phlegrean fields ash. Whether other deposits produce equivalent biological communities and equivalent tobermorite growth profiles is a question that has not yet been systematically studied, for the same reason that most questions about Roman concrete remain incompletely studied. The funding has not been made available. In 2023, the same year that the MIT team published their findings on the biological component of Roman concrete, the global cement industry produced approximately 4.1 billion metric tons of Portland cement. To produce that cement required burning approximately 1.5 billion metric tons of limestone at temperatures above 1,400 degrees Celsius, a process that emits carbon dioxide both from the combustion of fossil fuels to achieve the required heat and from the chemical decomposition of the limestone itself. Cement production is responsible for approximately 8% of global CO2 emissions, more than the entire commercial aviation industry. These numbers are not a detour from the main story. They are a description of the economic and environmental stakes involved in whether the Roman formula gets adopted or doesn't. A construction material that lasts 2,000 years without replacement eliminates the replacement market. A material produced at lower temperatures using volcanic ash instead of kiln-processed limestone eliminates a significant fraction of the carbon emissions. A material that heals its own cracks eliminates the maintenance market. The total annual value of the construction, maintenance, and replacement work that depends on Portland cement's 50 to 100-year lifespan is measured in the trillions of dollars. This is not an accusation. It is a description of how industrial systems work. No one in the global cement industry woke up one morning and decided to suppress Roman concrete. No meeting was held at which executives decided that an ancient formula must be kept obscure. The incentive structure does not require that kind of deliberate decision. It operates automatically, through the ordinary mechanisms of capital allocation. Research funding goes toward improving the products that generate revenue. The products that generate revenue are the ones that require continuous replacement. Continuous replacement is what Portland cement provides. Therefore, research funding goes toward improving Portland cement. This allocation logic is visible in the data. The global cement industry spends billions of dollars annually on research and development, almost all of it directed at improving the performance, consistency, and production efficiency of Portland cement. The research that has produced the Roman concrete findings, Jackson's marine geology work, Montero's synchrotron analyses, Masic's materials science investigations was funded almost entirely by academic institutions and small government research grants. The total funding for Roman concrete research over the past 3 decades is a fraction of a percent of what the cement industry spends on Portland cement improvement in a single year. The barriers to adoption are also structural in a more specific sense. Hot mixed volcanic ash concrete cannot be delivered by a ready mix truck. It cannot be pumped through standard concrete placing equipment. It cannot be tested by the protocols that certify concrete for structural use in any major economy. It sets on a timeline that is incompatible with construction schedules designed around Portland cement's behavior. Every practical aspect of how modern construction works assumes Portland cement, a material that requires different chemistry, different equipment, different testing, different sourcing, and a different conception of what a building material is supposed to do over time, is not competitive in a market where the existing standard has 2 centuries of infrastructure, expertise, and economic momentum behind it. The Roman formula does not lack advocates. It does not lack evidence. It does not lack a mechanism or a documented record of extraordinary performance. What it lacks is a market structure capable of valuing what it offers durability measured in centuries, not decades against costs measured in the quarterly financial cycles that govern every firm in the industry. The carbon emissions dimension of this story deserves more attention than it typically receives in discussions of Roman concrete research, because it transforms the question from one about historical curiosity into one about present-day survival. Cement production is responsible for approximately 8% of global CO2 emissions, a figure that exceeds the emissions of all commercial aviation and rivals the emissions of all heavy industry combined. Every ton of Portland cement clinker produced requires heating limestone to 1,450 degrees Celsius, which releases CO2, both from the fuel used to achieve that temperature and from the limestone itself, which is approximately 40% CO2 by weight. A volcanic ash-based pozzolanic binder, produced without kiln calcination, would eliminate the process emissions component entirely and dramatically reduce the fuel emissions component. At 4 billion tons of annual cement production, the emissions implications of a partial transition to Roman formula materials would be measured in hundreds of millions of tons of CO2 per year. There is a particular absurdity at the center of the modern Roman concrete story that deserves to be named directly. 2,000 years after the formula was first used, multiple corporations and research institutions are attempting to own it. When Hendrik Jonkers at Delft University published his work on bioconcrete in 2006, his institution filed a patent on the specific formulation he had developed: bacillus bacteria, encapsulated in clay pellets with calcium lactate as a nutrient source, mixed into a standard concrete formula. The patent was legitimate. Jonkers had done genuine original work in developing a practical delivery mechanism for the bacteria and demonstrating its effectiveness in controlled conditions. His specific formulation was novel, even if the underlying principle, biological calcite deposition, repairing concrete cracks, was, as it would later turn out, 2,000 years old. The Jonkers patent was followed by a cascade of related filings. Research groups in the United States, Germany, China, South Korea, and the United Kingdom filed patents on variant bacterial delivery mechanisms, alternative bacterial strains with similar calcite depositing properties, modified pozzolanic concrete formulations, and processes for incorporating extremophile organisms into construction materials. By 2020, the intellectual property landscape around bioconcrete had become extraordinarily complex. A dense thicket of overlapping claims, boundary disputes, and licensing negotiations that made commercial development of any specific formulation an exercise in navigating legal terrain as much as material science. The formula that was common property of the Roman Mediterranean world, used freely by generations of builders across 3 continents, owned by no one, protected only by the guild system's informal secrecy, had been converted, through the application of modern intellectual property law, into contested private property. Multiple parties now claim ownership of variations of a process that Roman builders practiced without patents, without licensing fees, and without legal enforcement of any kind for 600 years. The practical effect on adoption is significant. A construction company that wants to pilot Roman formula bioconcrete on a specific project must first determine which patents apply to their intended formulation, negotiate licensing terms with each relevant holder, ensure that their specific application does not infringe on competing claims, and then repeat this process for any future projects. Academic researchers who develop improved formulations must route their work through institutional technology transfer offices whose primary function is to monetize intellectual property, not to facilitate adoption. The knowledge is available in academic literature. Its practical use is encumbered by legal complexity that has no equivalent in any pre-patent era context. There is a structural irony here that is difficult to overlook. The Roman guild system protected the formula through secrecy, a social and institutional mechanism that kept the complete formula within a defined community and prevented its general adoption. The modern intellectual property system has achieved a remarkably similar result, keeping the formula effectively inaccessible through legal complexity rather than social exclusion. The mechanism has changed. The outcome has not. The formula, 2,000 years after its peak use, remains practically unavailable to the builders who could benefit from it most. The legal complexity around bioconcrete intellectual property has produced a counterproductive dynamic that researchers in the field describe with consistent frustration. The most commercially promising formulations, the ones closest to practical construction scale adoption, are also the most heavily encumbered by competing patent claims, while the older, more fundamental work that established the basic science has long since passed into the public domain. This creates a situation where the scientific foundation is free and the practical application is locked. Research groups that want to develop commercially viable bioconcrete must either design around existing patents, a process that typically makes the resulting formulation less effective, or negotiate licensing terms that raise production costs to levels that make the material uncompetitive with Portland cement. The patent system, designed to incentivize innovation by protecting its commercial value, has, in this case, produced a landscape where innovation is thoroughly documented and practically inaccessible. Every significant public infrastructure project in the United States, the European Union, Japan, Australia, and most other developed economies is built to a specification that references one or more national or international testing standards. In the United States, the relevant body is ASTM International, which publishes standards for the performance, testing, and certification of construction materials. In Europe, the equivalent function is performed by the European Committee for Standardization, which issues EN standards. These organizations set the rules for what counts as a qualified building material, and those rules were written for Portland cement. ASTM C 150, the standard specification for Portland cement, requires, among other things, that a material achieve a minimum compressive strength of 2,800 pounds per square inch after 28 days of curing. This 28-day strength test is the central metric around which modern concrete specification revolves. Design engineers calculate structural requirements based on 28-day strength. Construction contracts specify 28-day strength. Quality control programs test for 2 8-day strength. The entire language of structural concrete specification is organized around a number that measures what a material can do within a month of being poured. Roman formula volcanic ash concrete does not perform optimally at 28 days. It performs optimally at 200 years. The properties that make it extraordinary, the ongoing tobamorite crystal growth, the biological self-healing mechanism, the densification that occurs in marine environments over decades, none of these appear in a 2 8-day test. A specification test designed to measure the properties of Portland cement is, by definition, unable to see the properties of a fundamentally different material category. Getting a new material accepted into construction standards is not impossible, but it is a process that operates on timescales measured in decades and costs measured in tens or hundreds of millions of dollars. Proponents of a new material must conduct multi-decade performance trials that produce data in formats that standards bodies can evaluate. They must fund the revision process, which requires consensus among dozens of technical committees, regulatory review by multiple government agencies, and acceptance by the insurance industry, which ultimately underwrites the liability that construction standards are designed to manage. They must then persuade construction firms, public agencies, and project developers to specify a new material that their engineers are not trained to design with, that their contractors are not equipped to place, and that their clients are not familiar with. This is not a conspiracy against Roman concrete. It is the ordinary behavior of a regulatory system designed to ensure that the materials used in public infrastructure meet a minimum safety standard before they are widely deployed. The system works as intended. Its unintended consequence is that it creates an enormous structural advantage for materials that are already inside the standards framework. Portland cement, and an enormous structural disadvantage for materials that are not, regardless of their long-term performance characteristics. The testing system cannot see what it was not built to look for. It measures 50-year performance in a 28-day window. A material whose advantages compound over centuries is, by the metrics that govern modern construction, indistinguishable from an inferior material. The formula has been rediscovered. The evidence of its superiority is documented. The institutional systems through which construction decisions are made have no mechanism for acting on that evidence, and so the Pantheon stands, 2,000 years old and structurally sound, while the bridges of the modern world are replaced on schedule, and the process continues exactly as designed. The 2 8-day compressive strength test has a history worth knowing, because it was not derived from any analysis of how long structures actually need to last. It was established in the early 20th century as a practical compromise between the time needed to get a meaningful strength measurement and the time available within normal construction project schedules. 28 days is long enough for Portland cement to develop most of its final strength. It is short enough that test results arrive before the construction phase they are meant to certify has concluded. It is not, in any sense, a measure of long-term structural performance. It was never intended to be. The fact that it has become the central metric around which all structural concrete specification revolves is not a consequence of its scientific validity as a durability predictor. It is a consequence of its operational convenience, and that convenience has locked the entire regulatory framework of modern construction into a measurement system that cannot see the most important thing about the most durable concrete ever produced. Every structure this story has visited: the Pantheon, the harbour walls of Caesarea, the submerged breakwaters of Pozzuoli, the aqueduct spanning the high plain above Segovia, was built with the same fundamental understanding, even if that understanding was never explicitly articulated by the people who built it. Those structures were not simply constructed, they were cultivated. Their builders initiated a process and then trusted the living world to continue it. This distinction between construction and cultivation sounds like a poetic framing, but it is a precise one. Construction produces a static artifact, an object with defined properties that it will possess from the moment of completion until the moment of its failure. Cultivation produces a dynamic system, an arrangement of materials and organisms and environmental conditions that will develop, respond, and change over time in ways that exceed the properties of any single moment. The Pantheon's dome is not the same material today that it was on the day Hadrian dedicated it. It is denser, more crystalline, more resistant to the specific stresses that time has applied to it. It has responded to its environment for 2,000 years and become stronger for the response. Modern materials science has, in the 21st century, begun to understand why this is possible at the fundamental level. Microbiology has established that virtually every natural material of extraordinary durability, old-growth hardwoods, deep-sea coral reefs, certain ancient limestone formations incorporates active microbial communities whose metabolic activity contributes to the material's structural integrity. These communities are not contaminants, they are participants. The microbiome is not a peculiarity of living tissue, it is a feature of any system that has been given enough time and biological complexity to develop one. Roman concrete, viewed from this perspective, was not an anomaly. It was an application, the most sophisticated ancient application known to science, of a principle that the natural world had been demonstrating for billions of years. The durability of living systems is not an accident of chemistry. It derives from the presence of biological agents capable of responding to damage, repairing it, and adapting to the specific stresses that time delivers. Every material humanity has produced that matches this durability. Damascus steel, the varnished wood of Stradivarius's instruments, the fired ceramics of certain ancient kilns has involved, in some form, the incorporation of biological process into material production. And every one of those traditions disappeared without a complete written record. This is not coincidence. The knowledge that connects human making to living biology is precisely the knowledge that guild systems most carefully protected, that written records most consistently omitted, and that institutional collapse most completely destroyed. It is the knowledge that sits below the level at which most technical description operates. It is the knowledge that requires not just information, but relationship. A sustained, embodied familiarity with living materials over long time periods that cannot be compressed into a manual or transmitted through a text. Modern construction has spent 2 centuries building in defiance of this principle. Every biological component in modern construction materials is classified as a contaminant and systematically excluded. The concrete is sterile. The steel is protected from any microbial contact. The building envelopes are sealed against the introduction of any living organism. This is not ignorance. It is the deliberate application of a philosophy. The philosophy that the most reliable materials are the ones most completely under human control, that the Roman harbour walls have spent 2,000 years demonstrating to be incomplete. The convergence evidence from multiple ancient traditions is worth stating explicitly, because it transforms the Roman concrete story from an isolated historical anomaly into part of a broader pattern. Damascus steel was produced by a tradition that understood, empirically, that certain iron ores from specific geological regions, likely ores with naturally high carbide, and trace element contents from microbially active geological deposits, produced blades that could not be replicated from purified feedstock. Stradivarius's wood was treated with mineral biological solutions whose composition has still not been fully reconstructed. Chinese silk production in the Han Dynasty involved specific cocoon fermentation processes whose microbial components were maintained through continuous production rather than documented formulas. In every case, extraordinary durability, biological component, oral transmission, catastrophic loss when the tradition was broken. The pattern is not Roman, it is human. The research groups pursuing bioconcrete and related biological construction materials in the early 21st century did not begin their work with Roman concrete as a reference point. They arrived at the same destination from different starting points, driven by different questions, working with different materials and organisms and institutional frameworks. That they all ended up in the same conceptual territory building materials that incorporate biological self-repair mechanisms is not because they were following Rome's example. It is because they were following the same underlying logic that Rome had followed 2,000 years earlier. The logic of working with living systems rather than against them. Hendrik Jonkers at Delft embedded bacillus spores in clay pellets and mixed them into standard concrete. When cracks formed, the pellets broke, the spores germinated, and calcite sealed the fracture. Pilot applications in Dutch infrastructure have been ongoing since approximately 2015, with results that consistently outperform standard concrete in crack resistance and long-term durability. The mechanism works. The adoption curve is shallow. At the University of Bath, a team developed a variant using different bacterial strains and different nutrient delivery mechanisms, achieving faster activation times and more consistent repair in variable temperature conditions. Their work has been published, cited, and not yet built into a single major infrastructure project. At the University of Colorado Boulder, researchers have been exploring the broader category of biomineralized materials, construction substances produced by or enhanced through biological activity, with results that suggest the principle extends far beyond concrete, to structural ceramics, synthetic bone materials, and geopolymers. The DARPA program on biological fabrication of construction materials has, since roughly 2018, been exploring the military applications of self-repairing structures in environments where maintenance is impossible. Each of these programs is, in its specific formulation, a rediscovery of what Roman volcanic hillsides contained as a natural condition. The pattern that emerges from this landscape is striking. Multiple independent research programs across multiple continents, working in multiple institutional contexts, have each arrived at the same finding. Incorporating biology into construction materials produces outcomes that purely mineral approaches cannot match. Each program has validated its results in controlled conditions. None has been adopted at construction scale. The formula keeps being rediscovered. It keeps not being used. This is not a statement about the quality of the research or the competence of the researchers. It is a statement about the distance between knowing something and building the institutional infrastructure needed to apply it at scale in a world organized entirely around a different approach. That distance, in this case, appears to be approximately 2,000 years and counting. Somewhere in the Phlegrean fields, above the Bay of Naples, the volcanic ash that Roman builders mined for 6 centuries still sits in the same geological deposits. The same microbial communities are in it that were in it when the first Roman builder brought a sample to the Bay of Baiae and mixed it with lime and seawater and watched what happened. The formula has not changed. It has been waiting, with the patience of organisms that have been living inside stone for hundreds of millions of years, for the human institutions that surround it to catch up. The DARPA Biological Construction Program merits specific attention because it represents the first time a major government defense establishment has formally invested in the idea that biology and construction materials are not separate domains. The program, which began funding research around 2018, explicitly cites the challenge of maintaining and repairing infrastructure in remote or hostile environments where conventional maintenance is impossible. A challenge that the Roman harbour builders solved 2,000 years ago by building infrastructure that maintained itself. The fact that the United States military has concluded, based on its own operational requirements, that self-repairing biological construction materials are a priority, worth funding, is a different kind of validation than academic peer review, and it suggests that the moment when these materials transition from laboratory curiosity to practical application may be closer than the conventional construction industry's resistance implies. Return, at the end, to where this began. The Pantheon at dawn. The column of light descending through the oculus, moving across the ancient floor, measuring hours in a building that has been measuring hours longer than any other enclosed space on Earth that is still being used for its original purpose. The Romans who built it are dust. Every one of them, the laborers who mixed the volcanic ash, the engineers who calculated the dome's geometry, the emperor who commissioned it and gave it to the gods, has been gone for 16 centuries. The empire they served has been gone for 15. The language they spoke, Latin, has no native speakers anywhere in the world. The religious practices the Pantheon was built to serve have not been actively practiced for over 1,000 years. The building stands, and inside its walls, inside the concrete that carries the weight of the dome, and has been carrying it since before the fall of Rome, before the rise of Islam, before the Crusades, before the Renaissance, before the Industrial Revolution, before 2 world wars, bacterial endospores are still doing what they have always done, finding the hairline cracks that temperature and stress open, germinating in the moisture that enters them, depositing calcite, sealing the fractures, returning to dormancy. The building heals itself, invisibly, continuously, in increments no human eye can observe. The Romans embedded in their greatest structures a kind of biological memory, not metaphorical, but literal. A living archive, expressed in the chemistry of organisms too small to see, that has outlasted every other archive those builders left behind. The political memory of Rome lives in fragments of text and altered place names. The cultural memory lives in languages derived from Latin and legal codes derived from Roman precedent. But the biological memory, the memory encoded in the organism sleeping inside the stone, lives in every Roman concrete structure that still stands. It is the most durable record of the Roman world that exists, and it took 2,000 years to read. What this story leaves behind is not a lesson, exactly. It is a question. The modern world has, in the past 30 years, rediscovered the principle that the Romans applied. The mechanism is documented. The material is reproducible. The evidence of its superiority is overwhelming and peer-reviewed. And the infrastructure of the modern world, its regulatory systems, its financial models, its supply chains and testing protocols and institutional inertia, is organized entirely around a material that lasts 50 years and must be continuously replaced. An ingredient was erased. A formula was lost. The consequences have been accumulating in the form of failing bridges, crumbling seawalls, deteriorating harbor structures, and the carbon emissions of an industry that replaces what it builds on a schedule calibrated to financial quarters rather than millennia. The formula is not gone. It never was. It has been sleeping inside the stone all along, as patient as organisms that have been waiting inside concrete for 2,000 years can be patient. The only question that remains is whether the modern world, confronted with something it has forgotten twice, once through collapse and once through choice, has the institutional wisdom to remember it for good. The Pantheon will almost certainly still be standing in the year 4000 CE, assuming no catastrophic geological or human intervention. The highway bridge built 3 miles from it in 1960 will almost certainly not be. This is not a prediction. It is an extrapolation from documented material behavior. The same behavior that the MIT team confirmed in their laboratory, and that Marie Jackson's team confirmed in Mediterranean seawater. The structures that the modern world builds today will be replaced by the structures that the generation after us builds, which will be replaced by the structures that the generation after them builds, in an endless cycle of construction, deterioration, and replacement that consumes resources, generates emissions, and produces exactly the continuity and infrastructure that civilization requires, just at a cost, and with an environmental footprint that Roman concrete, had it been understood and maintained, would have made unnecessary. That is not a romantic claim about the past. It is a precise economic and environmental statement about the present.